Hello and welcome to week 4, and in week 4 we're going to start looking at what's called the expected value of a random variable. So far we've been thinking of looking at discrete random variables. We describe discrete random variables using the range of values it takes and the probability with which it takes each value in the range, right? The so-called PMF, the probability mass function. So once you have the values that it takes and the probability with which it takes these values, we see there are different types of distributions. We saw so many different distributions that show up there, and one can look at it that way. That's possible. So oftentimes there is a need to summarize the random variable into one number, right? So you might want to say, instead of describing the whole distribution, instead of describing the whole range, you might want to succinctly describe the random variable as one number, or describe it in some very small detail as opposed to the big detail of the distribution. Okay, so expected value is at the heart of it, and it has so many different utilities, and it's one of those important connections between data and probability theory. This notion of an expected value, everything has a connection, but this one is really closely connected to everything. Okay, so let's start looking at what expected value of a random variable is, and then go ahead and keep making those connections as we see them. Okay, we'll begin with a brief introduction, and the basic goal from a high level, okay, before we embark on expressions and derivations with expected value, from a high level, what is it? It's about summarizing data. If you have a large amount of data and somebody wants to know some summary information about it, right? Instead of giving every possible value, you might want to say, the data is in this range. It has a minimum value, a maximum value, a certain average value, maybe a certain median value, right? So things like that. You give some descriptive statistics or summary information about a large set of data. This is very common. You might have studied this in statistics 1 as well. So in particular, let's look at this average value a bit more closely. So the average value is quite useful. You see all over the place, instead of giving a lot of data, you just give the average. If you want to know a sense of how well a class is doing, you simply ask for the average marks of the class, right? So that gives you a sense of how well it is doing, instead of looking at the whole distribution and trying to figure out something. Same thing with any other sports or any other numbers that you want to look at. People always are talking about rate, right? The average number of runs this batsman can be expected to score in a innings, right? So things like that are very common, and it gives us a sense of how good the batsman is. Okay, so quite often this is very useful, and I can keep talking about the average and why is it's so useful and all that, but it turns out in probability theory, this notion of an expected value of a random variable is sort of a theoretical construct. It's introduced with a certain definition. It represents the average value that the random variable would take. Okay, so if you were to observe that same random variable a lot of times and you take the average, you will sort of get this expected value. That's one of the reasons why it has a good connection to practice. I'll talk a little bit more with specific examples later on as we go through in this class. But first thing we have to understand is the simple mechanics of it. What is the expected value? The random variable is given, the range is given, the PMF is given. How do you compute the expected value? After you compute the expected value, what are the basic properties of it? Can you simplify the computation? Can you do something with it? So those are the sort of basic mechanics of using expected value that we will see in this lecture, and then later on we will slowly connect it to this notion of its average value. Why is it connected to the average value? We'll see later on. Okay, so that's the introduction. Let's jump into the definition. Okay, before the definition, let me also motivate this notion of why expected value is something interesting with this very simple example. So let's imagine there's a casino and somebody wants to bet on something there in the casino, and here is this game. There is two dice that's being rolled, and the sum of the two numbers that you see, you can place a bet on it. This is a very common bet that a lot of people make. Okay, it's a very popular game, by the way. So here is the return. If you bet under 7 and you win, you get your money back. Okay, if you bet over 7 and you win, you get your money back. If you say equal to 7 and you win, you get 4 times the money back. Okay, so this is the result, and you can do some basic calculation with it. Supposing you bet 1 unit of money on under 7. Okay, what is going to be your gain and what's the probability of that. Okay, you can do this calculation. If you bet under 7 and if you actually win, you have a gain of 0, right? Whatever money you put in, you got back, right? Your gain is 0. And that has a probability of 5 by 12. This needs a bit of calculation. I'm not going to do it. Take it as a homework problem if you like. You throw a pair of dice. What's the probability that the sum is less than 7? Okay, strictly less than 7, you'll get an answer 5 by 12. But if you bet under 7 and the number is actually equal to 7 or greater, you lose, and in that case your gain is -1. Okay, you've lost money, right? And that happens with probability 7 by 12. You can do a very simple calculation there. Once again, 1 minus 5 by 12 is 7 by 12. You get that. Okay, same thing happens with over 7. The probabilities are the same. You bet over 7, your gain is 0. If the number is actually over 7 and the probability that a number is greater than 7, the sum is greater than 7, is 5 by 12. You can do this calculation and you can convince yourself that's true. Okay, same thing with -1, you get 7 by 12, and equal to 7 on the other hand, with probability 1 by 6. 1 by 6 is the probability that you get a number equal to 7. Okay, 7 comes in 6 possibilities divided by 36, 6 by 36, 1 by 6. Okay, in that case you get +3, but then you get -1 with the probability 5 by 6. Okay, so this is the scenario. So now you can ask a lot of questions about this, right? So how is it that the casino set up this problem, and how do you go about betting, right? So these are all questions. Should you play this game? Is this a reasonable game? Can you expect it? Can you expect that you will actually gain money at the end? Okay, or is it so bad that you're definitely going to lose if you keep on playing for a long time? Okay, so these are the kind of questions that are crucial. So like I said, why is it the casino decided to give returns like this? Why is it giving money back for under 7 over 7, and why is it giving 4 times the money back if it's equal to 7? And in the long term, if you keep on playing this game again and again and again, what can you expect to gain? Will you expect to gain something? Is it going to be positive? Is it going to be negative? Is it going to be 0? So these kind of questions are very, very crucial, isn't it? So this expected value or average value is tied to these kind of questions. So it's important in a problem like this to understand the average value, right? So that's more important than anything else. You may say, okay, the distribution is important, that is important and all that, but really what's important and finally in these kind of games or in many such situations is long term, when I keep on doing this, what can I expect to gain? What is the expected gain? What is the average gain that I would have got after all of this? So this might be something interesting, and that has a lot of meaning in practice. Okay, so hopefully I've convinced you that the average value is important for so many different reasons. Now hopefully let's jump into the definition. Okay, so here's the definition. It's actually a very simple definition, and it's very easy to write down. It's also quite easy to understand the definition. Okay, so let's say you have a discrete random variable x, the range is t sub x, and the PMF is f sub x. We've been talking about how range and PMF are central in describing a random variable. That's what is given there. So the expected value of x, we will denote it in this notation e square bracket, and I'll put something inside. Whatever I put inside, e square bracket, that is expectation of what's inside that. So in this case I've put x, so it's the expectation of x. It's called expectation of x, it's called expected value of x. I'll use both sort of interchangeably, but I think expected value of x is probably a better terminology. You might want to stick to that. The definition is very simple. You sum over every value in the range. Okay, so you sum over every value t that your random variable can take, and then multiply it with the probability with which it takes the value t. That is fx of t, right? So what is fx of t? As you know, fx of t is, let me make sure the choice is right. So this fx of t, so this is also equal to, in case if you want to write it down a bit differently, t in tx, t times probability that x equals t. So this might be also another equivalent way of understanding this definition. So that's the average or expected value, usually the expected value of the random variable x. Okay, so like I said, it has the operational meaning of if you observe the experiment. If you repeat this, you observe this random variable multiple times, several times independently, and then you add it all up and average it, you will get this something close to this. Okay, e of x. We will prove such statements later on, or we'll see results like that later on. But forgetting about all that, what it means in practice, the definition itself should be very clear to you, right? So how do you operationally execute this definition to compute the expected value given the range and the PMF? That should be hopefully clear to you. It's just plug it in. Given the range and the PMF, you can just plug it in and find the expected value. So once the PMF is given, once the distribution is given, the expected value is the same. So some people, for this reason, refer to E of x actually as a function of the PMF and not of the random variable itself. But it's very important to write it as E of x. You'll see why expected value of x is a very useful thing to have. Okay. A few remarks. There are other names. A lot of people use mean of x. Okay. So if you say mean of a random variable, it's exactly the same as the expected value of x. Some people call it the average value of x. It's not a very good, nice thing to say average value. It's better to say mean of x or expected value of x. So let maybe I should put a small strike through here to say that average value is okay. I mean, it's sort of clear, but maybe not a good terminology here. Okay. So we'll see some examples, and we'll see clearly this E of x, the average value, may or may not belong to the range of x. It may not be a value that x actually takes. Okay, even though it's the average value, it may not be a value that x actually takes, right? So it can happen. If you have 1 and 2, the average of 1 and 2 is 1.5. It's neither 1 nor 2, right? So it can happen like that. Okay. So usually people give units for the expected value. If your x has units, if your random variable is something you're measuring in a physical experiment, it has units, expected value of x also will have the same units. Okay, right? You're taking that same t and multiplying with the fraction of sort of probability with which it occurs. So it doesn't lose the units. You can keep the same units for expected value of x. Okay, quick definition. Hopefully you saw the definition. Let's see a few quick examples to see how you can easily do the summation given the PMF. Okay, here is this x, which is a Bernoulli distribution. You know what the Bernoulli distribution is, right? So the Bernoulli distribution is Bernoulli p. It's 1 with probability p, 0 with probability 1 minus p. Okay, easy distribution and very easy to compute the expected value of x. If you say expected value of x, it's 0 times 1 minus p plus 1 times p, right? Value it takes multiplied by probability with which it takes its value, and it just becomes equal to p. So notice for Bernoulli random variable, this is also equal to probability that x equals 1. Okay, so this is true only for Bernoulli, but for Bernoulli random variable, you see that works out as a very nice result. Easy, right? Very easy to sum, and similar such problems for other distributions are also very, very easy. Okay, so if x is uniform from 1 to 6, you know that it takes each value with probability 1 by 6. Okay, so if you want to do expected value of x, it is just 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6, 4, 5, 6, etc. So you just have to do this calculation, and that is just 3.5. Okay, so you can check that this is true. It's 3.5. Okay, and quickly you see in both examples, you got an expected value which was not clearly in the range, right? So in the first, for the Bernoulli case, you got an answer p, which could be 0.5, 0.7, 0.2, 0.1, like that, and the random variable takes only 0 or 1, and the random variable is uniform from 1 to 6. It took a value 3.5. It will definitely be within the range, but it won't be a value that it need not be a value that the random variable is taking. Okay. So here's another example. Supposing just to show this units aspect of the expected value, let's say somebody gives you a value of the lottery ticket as a random variable and describes the distribution like this. You remember the way I write this distribution, right? I write the value and I write the probability with which the random variable takes that value above it. Okay, this is a very simple way of describing the distribution. So here is a random variable which takes the value 200 with probability 1 by 1000, 20 with probability 27 by 1000, 0 with probability 972 by 1000. So you just take the value, multiply with the probability that with which the random variable takes the value, and add it all up, you get 0.56 as the total expected value of a lottery ticket. Okay, so most people will look at 200 rupees and say, okay, this lottery might give me 200 rupees, but look at the probabilities. The way the probabilities work, 200 happens with very low probability. So even though there is a possibility that you will get 200 rupees, the expected value of the random variable over a long term, if you take average, you will only make 0.56 rupees. So unless the lottery is 50 paisa or lesser, you're not going to gain. Even if the lottery is 2 rupees or 5 rupees, you're going to lose because your expected gain is only 0.56 while you would have spent so many rupees in getting the lottery ticket. Okay, so these are very important calculations. Before you buy a lottery ticket, you better do this calculation and know what the expected value is. Okay, here is one more random variable that I cooked up for just for showing you, I mean, just to show you that once I give you the distribution of the random variable, you can very easily find the expected value of it just by doing this, multiplying the value by the probability, adding it up, you get your answer. Okay, so that's fine. It's a simple example. But life is not always so simple, isn't it? It's going to quickly get a little bit more complicated, and let's begin with a slightly more complicated situation where I have a more general uniform case, but uniform in a sequence. Okay, so you have a random variable which is uniform from A to B, which basically takes A plus 1, A plus 2 till A plus B, till B. Okay, so it's uniform in a sequence of values from A to B. Okay, both included. Okay, if you now do expected value, you see that probability, since it's uniform, there are A to B is B minus A plus 1. So each thing is occurring with B minus A plus 1. Okay, everything is B minus A plus 1. So it's A times 1 by B minus A plus 1 plus A plus 1 times 1 minus B minus A plus 1, so on till B times 1 by B minus A plus 1. Okay, so now how do you simplify this summation? This 1 by B minus A plus 1 is showing up at the denominator. That's very nice. You can pull it out, but still you will be left with A plus 1 plus so on till till B. Okay. So when you want to add a sequence of integers, there is this very simple formula that you can use. It's B minus A plus 1 times A plus B by 2. Okay. There are various other formulae like this. So this is a very useful identity. You can use this and simplify this. So once you plug it in, you see that the expected value becomes A plus B by 2. Okay. So it's sort of intuitive, right? Why it should be A plus B by 2. You take values from A to B and it's all uniform. So the average value or the expected value should be A plus B by 2, and see how it ended up being in a very simple situation. Okay. So this example should already slightly give you the ideas of what can happen in these expected value computations. So if the summation becomes more and more complicated, you can get into some tough situations in finding the expected value. But if it's small and easy enough, we can do it. So what I'm going to do in the next 2-3 slides is take up some common distributions we've seen before. We took Bernoulli, we'll take binomial, we'll take Poisson, we'll take geometric, we'll take a few other distributions and try and execute this summation. Okay. So I'll go through a little bit fast, but I'll try to give you some reason as to why these summations work out. Very important is the final answer. Okay. The expected value, it's good to sort of remember by heart. In your mind, you should know what the expected value of the random variable is. Even if you don't remember every detail in the proof, it's okay. But the proof is also quite easy and interesting in its own way. It will also help you how to do summations. It's always an interesting topic. Okay. So let's start looking at more involved summations. The first thing we'll look at is geometric random variable. Okay, right? So you remember geometric, right? X is geometric means what is the random variable here? So x takes values 1, 2, 3, so on. It keeps on going all the way to infinity. And what's the probability which it takes value k? 1 minus p per k minus 1 times p. Okay, so that's the probability with which it takes value k. So if you do expected value, I have to sum t equals 1 to infinity, t times probability with which the geometric random variable takes value t, that's 1 minus p per t minus 1 times p. How do you sum this? Right, so what is the summation? It looks something like this, right? So it looks like p plus 2 times 1 minus p times p plus 3 times 1 minus p squared times p plus so on. There is this 2, 3, 4, so on, and 1 minus p whole squared, so on. Okay, so this kind of summation, and you see it's a little bit non-trivial. It's not immediately clear how to sum these things. Okay, so these kind of summations, even for the geometric random variable, these kind of summations can show up. And in the geometric random variable, it's good to know the expected value, right? Because what is geometric? The first time, it represents the number of attempts you have to make till you see the first success, right? So it's good to know if you're looking at it multiple times, what would be the average number, right? So expected value is good to know for the geometric random variable, and it seems like we have to do a non-trivial summation to get to it. Okay, so we'll do it soon enough, but I just want to show you how it can become non-trivial. So you go to Poisson, again you have the same sort of situation, right? this is the probability with which the Poisson random variable, just erase it, x equals t, right? It's e power minus lambda times lambda power t by t factorial, t times that, okay? So this is the summation we have to execute to find the expected value of a Poisson random variable. I already showed you how Poisson random variable shows up in practice. It's very useful random variable to know the expected value for, but to calculate the expected value, it looks like we have to do a complicated summation. We'll see it soon enough, but I just want to convince you first that it's a summation. It's slightly more involved than your typical summation. Okay, even if you go to binomial, it seems like one of the easy distributions that show up from repeated Bernoulli trials. You see the expected value is very confusing to calculate, right? So this is once again the probability that the binomial distribution takes the value t, right? When you have binomial NP, it takes the value t with n choose t, p power t, 1 minus p power n minus t, right? So this again, remember this, some of us may have written it like that. So this NCT I will denote also as n choose t, like this, okay? N choose t, I'll denote it like this, binomial n choose t. You know the formula for this, right? So this is just n factorial by t factorial times n minus t factorial, okay? So you see, even for the simple random variables or common random variables that we saw, geometric Poisson binomial, the summation is involved, okay? So if you go to the other ones like negative binomial and hypergeometric, it's going to get even more involved, okay? So how do you do summations like this? I'm going to quickly show you the proof and then show you the method for evaluating the summations, quickly give you the answer. Like I said, the answer is more important than the proof here, but it's also good to know the proof. It's good to know how to do these kind of summations, okay? So one crucial idea is this kind of a difference equation idea. Supposing you have a sequence you have to sum, right? You have a sequence that you need to sum, which is summation from t equals 1 to n at, okay? And this at satisfies this kind of a property, okay? At plus 1 minus r times at, okay, equals some other sequence bt, and this r is not equal to 1, okay? So this equals another sequence, this is another sequence. In general, another sequence, it could even be 0, I mean, it could be a trivial sequence, whatever, okay? Then it turns out this summation is given by this formula, okay? It's this a1 minus r times an divided by 1 minus r plus 1 by 1 minus r summation bt t equals 1 to n minus 1. This is actually very easy to prove. It's not very hard to prove. You just write down one equation after the other, and then you'll see that if you multiply by r and subtract etc., it will sort of nicely cancel and align up and add up, and you will get finally this an minus, you'll get this. This is not very hard to prove. I'm not going to prove it, but you can write this, and this is a very important ingredient in many of these summations, okay? So particularly geometric like summation, geometric progressions, you can solve using these means. So this is one idea. Another is the geometric progression itself. So in geometric progression, this bt becomes 0, okay? At plus 1 is r times at, okay? So you just every time you go to the next in the sequence, you keep multiplying by r, and that summation is just a1 minus r an by 1 minus r, okay? So if r is less than 1 and n is growing very, very large, this summation goes to a1 by 1 minus r, okay? So this a1 by 1 minus r is very important. When n goes to infinity, it's a1 by 1 minus r. Absolute value of r should be less than 1 for this formula to hold, okay? That's geometric progression. You also have this exponential function. This is a useful function to know, right? So this is basically nothing but, this is the same as e power lambda equals summation t equals 0 to infinity lambda power t by t factorial, okay? So you multiply both sides by e power minus lambda, you get this equation, okay? So this is the same property as that leads to the Poisson PMF being a valid PMF, right? So you add up all the probabilities of the Poisson random variable, you should get 1, no? And that happens because of this. So this is the exponential function. This identity is very useful, particularly when you want to work with the Poisson distribution. The first two are sort of useful when you work with geometric distribution. This one is useful for the Poisson distribution. For the binomial, this is very useful, okay? I think I referred to it once before. If you do a plus b power n, you can write it as k equals 0 to n, and then you will have the binomial looking formula. So n choose k a power k, b power n minus k. A particular thing to note here is, if you set a equals 1 minus p and b equals p, okay, right? If you set a equals 1 minus p and b equals p, the right hand side becomes 1. Okay, and what is the left hand side? Left hand side you will get the binomial PMF values. Okay, so summation k equals 0 to n, and choose k 1 minus p power k times p, okay, or maybe I should write it the other way around. It's okay, p power, maybe I should write it the other way around. Let me write it as a equals p and b equals 1 minus p. It's the same thing. Anyway, a plus 1 minus p is 1. So, p power k 1 minus p power n minus k equals 1. So, this is the binomial PMF adding up to 1, a very simple way of seeing it. So, these kind of things are very useful in the summation. Once again, I am going a little bit quicker, but hopefully you see that. So, now once you have those tools, okay, so these are the tools that are useful for simplifying these summations. Once you have those tools, it's easy to identify what the geometric PDF is. For the geometric summation, e of x is this summation. You can quickly identify that this follows the difference equation. Okay, so this difference equation with a1 being p, r being 1 minus p, and this bt being r power t into p. Okay, so you can check this. So if you let this to be at, okay, what is at plus 1? That's t plus 1 times 1 minus p power t to p. Okay, so if you do at plus 1 minus 1 minus p times at, you will get 1 minus p power t times p. This is what you get. Okay, so you can check that this is true. So this gives you the differential equation, the difference equation sort of picture, with a1 being p, r being 1 minus p, and bt being r power t into p. Okay, so once you plug it in, you'll just get the answer is a1 by 1 minus r, isn't it? So this is the answer, a1 by 1 minus r, and a1 is just p. Did I get it right? No, it's not a1 by 1 minus r, I'm sorry, it's a1 by 1 minus r plus this 1 minus r into summation bt. You have to do some work here, you just plug it in. I plugged in the wrong formula here, I need to plug in the difference equation. You do that and tend n to infinity, you will get 1 by p. Okay, so this 1 by p is very important. So expected value of geometric is 1 by p. Nice, isn't it? So in spite of this nasty looking summation, using some simple ideas, you're able to simplify and you get 1 over p. Okay, I didn't go into great detail here. You just plug this into the DE summation formula that you get and tend n to infinity, and you know that this r is less than 1, so r power n and all will go to 0. So you do all that, you'll get 1 by p. Okay, so expected value of a geometric is 1 by p. Geometric p, expected value is 1 by p. Okay, so that's the expected value. Okay, good to know. So now for Poisson, you have to do a little bit more trickery. So you have the summation t times e power minus lambda, lambda power t by t factorial. This t and t factorial will cancel. Remember, t factorial has a t in it, doesn't it? So 2 into 2 factorial, you can cancel the 2. 3 into 3 factorial, you can cancel the t. 2. So that's something you can do. So this becomes 1 factorial. This, if you want, you can cancel. This becomes 2 factorial, so on. And then you pull 1 lambda out. If you pull 1 lambda out, you're going to get lambda e power minus lambda. This will just become 1. This term will become 1. This term will become this. This term will become this, so on. Okay. And what you identify here is just e power lambda. Okay. So you get lambda times e power minus lambda times lambda, e power lambda. You simply get lambda. So once again, the most important thing is the expected value is lambda for the Poisson distribution. Poisson lambda, expected value is lambda. Right? Easy enough to understand. Okay. Now, if you repeat something similar for the binomial, I'm really not going to go into detail here. You can just go ahead and simplify. Finally, you will just get NP. So it goes once again to cancelling this t, right? You can cancel this t here. You'll get a t minus 1 factorial, and then you pull 1 n out. Okay. So it's let me skip the details here. So the big shot is once again that e power x is n times p. Very simple, right? So not e power x, expected value of x. Okay. So these 3 distributions, while they look a bit confusing if you have to do the calculation, the expected values are very, very simple. Okay, so these things you should just mug up and you should know these answers. For a binomial NP, expected value is NP, n times p. Okay, Poisson with parameter lambda, expected value is lambda. Geometric p, expected value is 1 by p. Remember one thing very careful about the geometric distribution, we are starting at 1. Okay, our geometric distribution starts at 1 and you get expected value 1 by p. A lot of people start geometric distribution at 0. I think it's not a good idea. Starting at 1 is the correct idea, I think. So 1 by p is good, but if you start at 0, you will do 1 by p minus 1. Okay, there will be a subtraction of 1. Okay. Anyway, so these kind of more involved summations will happen sometimes in expected value. Okay. So if you know the methods, you can go through it. But even if you don't know, you can just look up in Wikipedia or any of the other websites. If you just look it up, there will be a clear page on how this calculation is done, how the simplification is done, and how you get the answer for expected value of a random variable. Okay, common distributions, these things are easy to find. Okay. Okay, so I also wanted to show you the picture of the PMF and how where the expected value comes and sort of if you can see it. So let's say you look at a Bernoulli 0.3 distribution. It takes value 0 with probability 0.7. It takes value 1 with probability 0.3. Its expected value is 0.3, somewhere in the middle. Okay. And if you look at binomial 20, 0.3, the expected value is 6, isn't it? So this expected value is 0.3. Okay. This is expected value equals 6. Okay, 20 into 3. Okay, maybe I should write it like that. 20 into 0.3, which is 6. This is what we saw on the binomial. And you see the expected value is where the peak sort of the distribution comes. Okay, in some sense. That's not always true, right? I mean, see here is some 0.3. Where is the peak? I don't know. So here is a geometric distribution. Once again, the expected value is 1 by 0.3, which is roughly about 3.33, so on. Okay, so that's the expected value, and you can see this is the geometric PMF with 0.3 decaying. This is Poisson. Poisson once again, expected value of x is just lambda. This is 6. Okay, again this Poisson is looking so similar to the binomial PMF, isn't it? There's good reason for that. And you see that it has a nice picture and the expected value comes somewhat in the middle. So it's a good thing to sort of see where the expected value will be. Expected value will be definitely inside the range of the random variable, but it need not be a value that the random variable takes itself. It will be sort of, it appears to represent the peak of the PMF. If you had something like that, that's not a bad intuition, but clearly it's not exactly true, isn't it? Here is the geometric distribution, the peak happens at 1, but clearly the expected value is 3 point something. It's a bit away. It sort of represents the whole PMF in one number. So it will be somewhere in the middle. Okay. So hopefully this gave you a sense of the calculations involved in computing expected value given the distribution. It doesn't seem too hard, except that in some cases the summation may become a little bit complicated. Okay. So we'll stop here and pick up from here in the next lecture.